Hello everybody and welcome to the Carl and Cymru revision sessions. The session this evening will focus on topic 4 of Unit 1, which is focusing on bonding, and will be presented by Miss Stevens from e-sgol Bro-Peda. The session will last around 45 minutes where Miss Stevens will run through the relevant content. If you have any questions during the session, please use the question answer Q&A section and we'll do our best to answer you. You'll see that there's a hyperlink in the Q&A section. If you're happy to leave your name and email address, we would love to keep in touch with you so we can send you information about future events. You can click on the link at any time during the session. Today's session will be recorded, and the recording and any relevant resources will be uploaded to the e-sgol website under the Carl and Cymru tab. So thank you, Ms Stevens, and over to you.
So good evening to you all. Now, as was outlined by Mr. Black there, but also more specifically what he outlined in the first session that ran last week. If you haven't had a chance to look at that, or if you didn't join at the time, please take that time because it was a really good, useful session. But this is the advanced information that's been released by the WJC, which does explain why we've chosen to focus on what Mr. Black did last week, which is chemical calculations, as well as what I'll be doing this evening, which is the bonding. Okay, now there is important sessions that have already been done. For example, there has been an equilibria session that's been recorded previously for CADLAM. So please, if you want to have more explanation of that, then please look up that relevant session from previous sessions. Okay. So the specification, to a certain extent, the specification clearly outlines a lot of stuff that was previously done in GCSE, and you're just recapping and strengthening and building upon that information. But however, it is worth telling you that as an examiner, we are instructed to be far less tolerant in AS comparable to GCSE, so they're far less forgiving of kind of sloppy vocab and like wishy-washy kind of choosing of the words. Okay, so it is worth noting that yes, you have covered lots of this basic information previously, but it is no longer acceptable not to be very clear. So you're looking for clarity in your answers. You'll notice that there is the mention here for learning outcome H, which was the VSEPR principle. There has been a session, I think, it was presented myself back in spring 2022. So that entire session focused on VSEPR. So please do take that time to look back at that if you want clarity on that, because I'm going to be focusing this evening primarily on intermolecular forces and hydrogen bonding more than the VSEPR component of that topic 1.4. Okay. So, as I said, far less forgiving on the kind of clarity of your answers in AS and moving on to A2. And hence, I wanted to go through a few key terms with you because it will be instrumental in success if you can get these under your belt. It's also worth noting that there has been a misconception with certain pupils where they do say in the specification, no formal definition is required. Please take note, that does not mean you do not need to know what it means. It simply means that there isn't a word for word identical definition possibly, but it certainly doesn't mean that you don't need to know what it is. You do. Okay, so they ask you very commonly things like, what does the term dipole mean, or polarity? You need to know what they mean. So ionic bond, we did this in GCSE, but to be clear that it is a bond that's formed by the electrostatic attraction between positive and negative ions. It's best to try using those cationic and anionic terms as well if you can. Covalent, as we know, gives rise because you have a paired share of electrons. It is worth noting this is crucial. Okay, those shared paired of electrons need to be an opposing spin when they get shared between two atoms, otherwise they won't play ball. Okay, they will repel each other. That's the only way they can overcome that electrostatic repulsion, is by being an opposite spin. Coordinate bond, now this is new. Okay, so once formed, no different from a covalent bond, but it is formed where that covalent bond originates from two electrons from the same species or atom. Okay, so coordinate bond. Then you've got electronegativity, and I'm going to dwell on this quite a bit during the session because it is so central to so many of the underlying principles in topic 1.4. So electronegativity, there are lots of definitions out there. So like a measure of the electron attracting power of an atom in a covalent bond. I think the one I was taught myself was the ability of an atom to attract an electron cloud towards itself within a covalent bond. whatever sits with you and you will be able to recall and define with clarity, as I said, go with that one. But make sure you know what electronegativity is. Right, intermolecular, okay. It is very, very common in AS that we get errors in the sense that we've got pupils that get these mixed up. So there's a very, very big difference between intermolecular and intramolecular. So intermolecular is the bonding that holds molecules together. So that is between, it's like an international rugby match, I suppose. Intra is within. So it is that strong bond, and they're always going to be trumping the intermolecular ones. Intramolecular forces are much stronger, and that occurs within the molecule as opposed to between. Okay, Van der Waals. I'm sure you're sick of hearing about Van der Waals by now, but yes, I was asked by my pupils to have to spell his name correctly. We're not that strict on the spelling of Van der Waals, but ideally get it right, of course. Okay, but Van der Waals is that intermolecular force which arises from dipole or induced dipoles being created, valence shells. Okay. In GCSE, it's classic to call it the outer shell, but obviously, as the basis of the word covalent, you should have already been familiar before year 12 that valency or valence shell means the outer electron shell. It contains electrons, of course, but often also contains those vacancies that gives rise to its reactivity. Valency, the number of bonds an electron can make with other atoms. So if there are traditionally 2 electrons in the valence shell, then the atom tends to be able to form 2 bonds as a consequence of that. Okay, so those are the 3 main types of bonding that you came across in GCSE, of course. So that covalent, the ionic, and the metallic. Don't forget the covalent is split into 2 sub fields as well, of course, which is the simple molecular and the giant ones. But we're just going to build upon that and make sure that you've got very clear understanding of the bonding before we expand on the intermediate between the ionic and the covalent, of course. So ions, as you know, gives rise from a neutral atom losing 1 or more electrons. So that, as you can see, is the sodium being in group 1 will form the cationic species of Na+. Okay, if the atom chooses to be gaining electrons like the anionic species you see there, which is chloride, then it gives rise to a negative ion, of course. Okay, so an anionic species. So in GCSE, traditionally what you had was these classic before and after, I suppose, diagrams where you had the electronic structures of the atoms before they bonded, and then you clearly show the transfer of electrons within that system from, so clearly you start with the magnesium and you transfer across. So it's like the before and after in a sense, and then you'd have these kind of ions present at the end, showing the ionic charge, with it cationic or anionic. We'd show them with brackets traditionally in GCSE. So chlorine, the classic kind of covalent we've got there. So that gives rise because of the sharing, of course, and that's because 2 atoms that want to gain can't both satisfy by gaining, of course, so they share their valence shells. Okay, metallic bonding. So metallic bonding, as you recall, gives rise to nearly all of its metallic kind of traditional properties that you're familiar with. Now, when it comes to metallic bonding, it's a question that often is raising its head in GCSE, but certainly in year 12 when that kind of curiosity comes about, I suppose, is that I'm often asked, why are some metals more metallic than others? For example, why is aluminium a better, for better of a better word, I suppose, why is aluminium a better, more traditional metal than, say, sodium, which is in group 1? Well, those kind of properties gives all based around that sea of electrons, of course, isn't it? Okay, so as it says there, why does aluminium conduct electricity better than sodium, for example? That is a classic question that I got out of the WJC question bank. It was an AS question, and that question requires you to focus on that sea of electrons, on the fact that sodium, being in group 1, forms cationic species of +1, whilst aluminium in group 3 will form cationic species of +3. So it's a much more condensed sea of electrons, giving rise to much better conductivity, of course, for aluminium comparable to sodium. So, as I said, going back to the specification I showed you earlier, you've got lots to cover in this unit, but lots of it isn't new. Okay, so lots of it was building upon what you previously learned in GCSEs, and just tweaking and clarifying certain points about it. Okay, so I'm not going to stress you out by saying that there's lots of new stuff. I'm sure you're familiar with this because it was in Unit 1, of course. But lots of this is building upon GCSE. So chemical bonding, okay, regardless of what the type of bonding is, metallic, ionic, covalent, etc., it all hinges on this positively charged nucleus, which contains that protons, of course, and the negatively charged electrons arranged in such a way that the electrostatic attraction, pardon me, I had a real tickle in my throat then. So the electrostatic attraction can outweigh any repulsions that's created within that compound, okay, or molecule. So it's the core principle for any type of bonding. So ionic bonding, you know that one species will donate the electrons, becoming cationic, whilst another species will become anionic by receiving those electrons. So it's a give and take. They have to be interdependent. You can't have a cation being created without an anion being created somewhere else. Okay, so classically there I got the cartoon. So it's all about somebody giving up an electron because they don't really need it, and they become more stable and energetically stable. That is, by losing, and another species will become better and more stable by gaining. Okay, so sodium chloride, classic GCSE example of ionic bonding, you see there. I would like to draw your attention to something that is not an improvement then, but certainly something that has changed clearly from GCSE to AES, is the fact that we are now only focusing on the valent electrons. Some of you might have undertaken that principle in GCSE anyway, but please do not waste time drawing inner rings in AES. Okay, it has to be those just valent shells and showing the cationic and ionic species formed as a consequence of losing just the valence shells. That's why you can see here that the sodium looks like it's got no electrons, because we've only focused on the valent electron, which was that one electron in the first place. So that's not tweak them, but a slight discrete change that you might have come across. So ionic bonding, another thing I'd just like to quickly point out, okay, as I'm sure you're aware that an ionic bond in itself is simply an electrostatic attraction between any compound with ionic bonding in it, okay? Now, it is worth noting that there is often in AES a question that asks you to label a diagram. Okay, so they might not have given you this information, for example. They ask you, what is that, for example? Well, classically, anionic species are much, much larger than the cationic species present, and that's simply because when you form a cation, okay, the ionic radius shrinks, so it's smaller than the atomic radius of that atom itself. Whereas in an anionic species, because you're gaining that electron, then the ionic radius is actually much bigger. So if you're given a diagram, there are a few exceptions, but I won't go into them. You can pretty safely say that in a diagram of this nature here, that the larger of the two spheres that you see in the diagram would be the anionic species present. Now that is clearly sodium chloride, so it's got a coordination number of 6,6. So coordination number, of course, comes in this next topic. I think it was 1.5 that you study coordination numbers. Okay, so ionic bonding, please be clear how to label a diagram. Be able to recognize it quite quickly as well is beneficial. Okay, so another example you can see there, it can sometimes get overly busy, and if you see here, even with the valence electrons alone being considered, it's quite a busy, kind of congested looking diagram. So we'll often see in AES is that we don't bother with the before pictures. It tends to focus just on the final picture that you see there. So it would focus primarily on just the after picture, okay? And that is usually perfectly fine. I would take guidance from the number of marks allocated. If it's a significant number of marks, then you'd probably be foolish to not give the before or the atomic structures. But most of the time, you're just looking for the compound being created or the molecule created. Okay. So covalent bonding. This is what I want to make sure that you are very clear about at the end of the session, is that covalent bonding as it was in GCSE, you understood is a pair of electrons being shared between those atoms, but they have to be in opposite spin. Now you are familiar with the electronic configuration and how they occupy the s, p, and d orbitals. You have to appreciate, therefore, that when covalent bonding comes about, they have to pair opposite to each other with respect to spin. Okay, otherwise they will repel and the electrostatic repulsion is too great and they won't bond. Okay, so you've got here, oh, sorry, I skipped that too quickly, fluorine. Okay, in this case, fluorine's only got one vacancy in its p orbital anyway, so that would be a single covalent bond, and that explains to you why fluorine in period 2 can only bond once, because it's only got one unpaired electrons that it can then bond. Okay, so dot and cross, these haven't varied massively in GCSEs. I would just say that we now don't bother with the rings. We tend to just go for the electrons. We still stick to the dot and cross, and it's important you do still show the difference between what belongs to what atom using the dot and cross, and in some cases even 3 different types of symbols. Then it is important that you possibly save some time by not putting the circles in. You wouldn't be penalised for them, but you'll hardly see them on mark schemes either. And it's usually best to look at what the mark schemes show you, because that's what they're expecting to see from you. Okay, so you got ammonia there, the classic one, water classically, methane, or these are all examples that you would have done in your sleep, hopefully at GCSE. The double bonded, that was the tweak, I suppose, in GCSE, wasn't it? Is that you have to be familiar with double bonding. But of course, now, hopefully, you appreciate, and you knew it in GCSE, you always appreciate that nitrogen was diatomic. But because nitrogen's in group 5, that does mean, in fact, that you get the creation of a triple bond in this case. So if you look at the overlap between the nitrogen and the nitrogen, there's actually 6 shared electrons there, so 3 pairs. So it's a triple bond in nitrogen. Okay, right. Just to give a bit more clarity, hopefully, to this carbon, we know that carbon forms 4 bonds. Okay, you knew that. It's the methane classically forming CH4. But if you look at the elemental configuration, then actually you've only got 2 unpaired electrons, and because you need this opposite spin, you need as many electrons unpaired so that you can pair them opposite each other as you possibly can. So what happens in carbon is that you have the promotion, I suppose, from the 2s to the 2pz orbital, and that then, if you notice, frees up 4 unpaired electrons that you can then pair up in opposite spin to bond covalently 4 times. Okay, so that's just showing a bit of a different interpretation to it, but please appreciate that in carbon specifically, because it's so central to a lot of the chemistry you do in year 12, is that there is that promotion of an electron from the S to the P, and that's what gives rise to this ability to bond 4 times. Okay, so coordinate bonds. This is a covalent bond, as you know, hopefully, where both electrons originate or come from a single species or a single atom. Okay, the condition for being able to coordinately bond is that you have to have a lone pair, so an unbonded pair of electrons in that donating atom. They do not have a lone pair of electrons, they cannot coordinately bond or datively bond, just to throw that into the mix to show my age. We were taught it as a dative bond. It's now noted as coordinate, but they mean the same thing. So if you come across that in literature, dative bond simply means coordinate. Okay, so there are lots of examples, and when you get to A2, hopefully all of you continue on to A2, you'll see even more examples of dative bonding that explains things like the Al2Cl6 formation of the dimer for aluminium chloride. Okay, but you can see that this is the dimer. So you've got the lone pair of electrons on the chlorine that then coordinately bond to that electron deficient aluminium down here. Okay, so coordinate bonding, hopefully that isn't going to throw you too much. But let's be clear, I said it earlier, I think, but once created, a dative or coordinate bond doesn't break up any more easily or more difficult than the other covalent bonds present. So there is sometimes a misconception that a coordinate bond is either weaker or stronger than the other covalent bonds present. It's not true. Okay, once created, it isn't likely to break up easily or less easily comparable to the others. Okay, right, metallic bonding. I touched upon that already, and the fact that you need to be quite confident in explaining certain properties. So if I ask you in year 10 for classic properties, most of you would have thrown the same properties at your teacher. I'm sure would have been things like, oh, it's malleable, it is ductile, it's a good conductor. Well, all of these properties originate from the fact that you've got this delocalized sea of electrons, okay? You have to be AS confident in explaining the properties of any metal. Because often, as I say, there's a comparison as well, which means why is this more metallic in most people's opinion than other metals example. So be confident. Go back and be clear in your head what gives rise to ductility, what gives rise to malleability, what gives rise to conductivity. Okay, all of these underlying principles have not changed since GCSE, but be confident in regurgitating, I suppose, and just explaining properties confidently within an AS exam. Okay, so what I need to focus on now for a brief period of time is the fact that very few compounds are purely ionic or purely covalent. Okay, most substances contain bonds that are a bit intermediate, so a bit of both in character. So they show a bit of covalent nature and they show a bit of ionic nature in their bonds. Okay, these are called polar bonds, and the degree of ionic or covalent bonds depends on that electronegativity. Now, you're not expected to memorize electronegativity, but this number should mean something to all of you by now, I hope. So it's like the magic number that you use as a guidance to whether something is primarily ionic or primarily covalent in nature. So if the difference in electronegativity is greater than 1.7, it leans towards being ionic in nature. And if the difference in electronegativity is lower than 1.7, it tends to be primarily covalent in nature. If it's close to being a difference of 1.7, then it's really going to be an intermediate bond that you're going to see. The greater the difference, the greater it leans towards one side of that spectrum or the other. Okay. So electronegativity, as I said, you're not expected to memorize these numbers, but two things you are expected to learn is the trends. Okay, so you're expected to learn that these are where the most electronegative lies. So top right. Okay, top right, those are the most electronegatives. We just do not take notice of those, which are the noble gases, of course. You'll often hear, myself included, if my pupils tune in, that that term electropositive, so the direct opposite of electronegative, they lie to the bottom left. Okay, now, as I said, do not stress too much about learning the exact numbers of any of them. Okay, but that doesn't mean you cannot be very, very foolish, I suppose, if you do not memorize the top three, the top dogs, as I call them in my lessons. So you're expected to recognize that fluorine is the most electronegative, followed by oxygen, followed by nitrogen. And they are obviously what drives things like the hydrogen bonding that we have. Okay. So if they're equal electronegativity, then they have an equal or share, I suppose, an equal ability to show that. Okay, so they share nicely, equal electronegativity. It's a non-polar covalent bond, but if they have a difference, then one of them will clearly take an uneven distribution of that charge, so an uneven share of that charge, and that electron density in that compound then lie towards that electronegative element. Okay, so you've got the classic non-polar covalent bond there. Okay, but you obviously got the covalent bond, and classically there you've got the HCl that looks, often when we sketch it, looks a bit like a teardrop in the direction of the chlorine, which is the delta negative, of course. Just because it does touch upon one of the questions later on, if I get to it, is that you have to also be confident in sketching the electron distribution in an ionic bond. Okay, and in an ionic bond, that electron density lies around the nucleuses of the ions, whereas in the covalent bond, there is, yes, there is some electron density around the atoms themselves, But there is also, and the main electron density on distribution will be between those molecules. Okay, so an ionic, do not forget, you are expected to be able to sketch that as well. Okay, right, so there are a few examples there. I'm not going to dwell on them. So dipoles and induced dipoles, of course. Okay, now these, I'm sure you've heard of the term van der Waals, but if you have what should be a polar bond, for example, between chlorine and chlorine, iodine and iodine, then yes, primarily it is a non-polar molecule, but there will be, with greater number of electrons, a shift towards a stronger van der Waals force being present, and that gives rise to high melting points, etc. Okay, it is worth noting, I should have said it earlier on that definitions one, intermolecular forces, they are what drives physical properties like boiling point, solubility, etc. The intramolecular bonds, that is what drives the chemistry of a substance. Okay, hydrogen bonds. Now these are special intermolecular forces, as I'm sure you're aware. They occur between molecules that have to be a molecule that contains a bond between a hydrogen and those top three that I mentioned earlier, which is fluorine, oxygen, or nitrogen. Okay. So because fluorine, oxygen, and nitrogen are highly electronegative, what that gives rise to then, also based on the fact that hydrogen is obviously very small, is that the delta positive charge is in the bonded hydrogen atom is spread over a small volume, and so it has a high charge density. And the highly polarizing hydrogen delta positive then attracts a lone pair of electrons from a highly electronegative atom in another molecule. So there has also been, over the years, some misconception over the fact that hydrogen bonding can occur between hydrogen in one molecule and an oxygen in another, maybe. Be clear, hydrogen bonding has to have the hydrogen bonded to one of the three electronegative ones in anything that hydrogen bonds together. Okay, so having a single O in one and a single H in another compound doesn't mean that they can hydrogen bond. They have to be bonded together within those compounds or substances as well. Okay, so that is how it would look. We represent them with dotted lines between them often. Okay, but how does this affect its chemistry? Because obviously it does. So what effect does these hydrogen bondings have? Okay, well, the effects are that, as I said earlier, it increases the boiling temperatures or boiling points. Okay, and also the other major change is that it increases their solubility. Okay, so we've got hydrogen bonding. You can see there, water is a classic one, of course, because you've got H2O. So obviously that oxygen being electronegative is bonded to the H. Hydrogen fluoride, okay, is also another compound that very clearly shows hydrogen bonding, and it does affect the boiling point of water and HF, comparable to its counterparts in the same group. Okay. It is also worth noting, I'm not sure how many of you do biology, they do tend to go hand in hand, but hydrogen bonding is also what drives that very interesting bond in DNA, the shape of a DNA, which you might have been taught is a double helix, okay? And it's hydrogen bonding that creates that double helix shape that you might recognize in DNA, okay? Right, moving on to the main bit I wanted to get to, which is, yes, I've very quickly, and apologies if it's been too quick, but feel free to pause at any point or go back, because obviously the materials will be available to you through that website. But I think it's really important not only to know the knowledge, but recognize when you need to expand on your answers and when sometimes concise, short, sharp answers are exactly what you need. Okay, so starting with the easy, except I'm sure you recognize no questions are easy at AS chemistry. But 1 mark short, sharp question, like a classic section A question, I would say. So put the following in orders of increasing strength. Well, the first thing to focus on there is that is an intramolecular or bond, okay? It's not inter. So that automatically has to be the strongest of the 3, okay? Then when you look at these two, these are intermolecular forces, of course, and therefore will be weaker than the covalent bond. So automatically you should be able to put covalent up here. Okay. Now, what then happens is that you should recognize that from the 2, and I have touched upon both, but I suppose I've done a bit more on hydrogen bonding, van der Waals is the weaker of the 2. Okay. if I took it as being simplistic numbers, you could probably say that a van der Waals force is 10 times weaker than a hydrogen bond, and a hydrogen bond is about 10 times weaker than a covalent. It's not perfect, and it's certainly a bit of a rough guesstimate there for you, but it does give you that mental check. Maybe hydrogen bonding is certainly much stronger than van der Waals. So that would be the middle one. So you've got hydrogen bonding in the middle. And then, of course, you've got the weakest one, which is the van der Waals. Okay, right. So that is a classic 1 mark, short, sharp. Don't dismiss short, sharp questions, though. They will get you. If you build up enough of those marks, they do pay dividend, of course. So yes, I know it's only 1 mark, but every mark is valuable. Okay, so I've also tried including, and I might not dwell on them all the time, but it will certainly be in the PowerPoint if you go back and revisit it. I've tried including any significant examiners' comments for you as well. And it is worth noting here that a lot of candidates, okay, did get the question right, but there was also a significant minority that thought that hydrogen bonding was the strongest, because it is not shoved down your throat to them, but it's very much emphasised that hydrogen bonding is much, much stronger than van der Waals. Some people did get lost then in being able to recognise where does the covalent bond lie therefore. Okay, so in that sense, just recall that intra is always going to trump an intermolecular force. Okay, right, so moving on to the next question. There was a drawing of a dot and cross diagram to show the bonding in calcium fluoride. Okay, now it's only 2 marks. Okay, so let's not go overboard in thinking, do I need to do the before and the after? The answer is no. Okay, what they're looking for here is that you've got the correct valencies at the end, the right number of electrons at the end, and more importantly, because it does tell you at the end of it, give any charges. They're trying to help you out, bless them. They want you, therefore, to put the forces in. So you've got the fluorine there. This is where it is really important that you remember to allocate different numbers or different representations of electrons in one species comparable to the other. Okay, calcium. Okay, you're only concerned about the valency on the outside, so we don't really care about that one. But it does show that being in group 2 will form cationic +2. Fluoride, therefore, is minus. And then you've got the identical in here. Now, this is where the significance of the dot and cross come from. Because you're not showing the before, it is assumed, therefore, that because you've shown the bonding as a dot in one, the presence of those tells the examiner that you understand that that must have originated from something other than the fluorine, because the fluorine's got its own crosses. But then, of course, the 2 dots must have originated from the calcium, therefore. So it's just showing discrete little things there, but important nonetheless. Okay. Right. This is worth noting.
Miss Stevens,
okay?
Can I ask a question?
Of course you can.
Yeah, I've got someone on the chat. So do you not have to show the atoms beforehand then? You can just show them after?
No. Because in GCSE it was classically worth or credited with more marks, the before was necessary. There have been, I've looked at the question bank, a few very rare times where they've allocated 3 marks for this type of question. Take a judgment, okay, from how many marks. I would say 90% of the time in an ionic bonding representation, only the after, shall we say, is needed. Okay, so only the ions formed as a consequence of the bonding already taking place. Okay, so if you represent it properly, the diagram says what's happened in itself. Okay, hopefully
fantastic.
That's clear.
Thank you.
So with this next question is, again, building on GCSE, and that sometimes makes people nervous. Okay, so this question was asking about a comparison, and that's what I need you to say there. Okay, judging the type of question is a key skill that you're gonna have to get under your belt. Okay, so this question was saying, give an observation that shows the difference in reactivity with cold water between sodium and potassium. Now, nearly all of you have seen that in real terms in the lab. I'm sure your teacher would have shown you this classic example, but you have to have a comparison, because that's what this keyword here is. Reading the question, interpreting what it means. So most people can say that potassium bursts into a flame, but unless you back that up by saying that the sodium doesn't catch fire, you do not get the credit. Okay, so that is important. You recognize what is being asked of it. The next question that led on from that was, describe the trend in the first ionization energy of group 1. Well, first off, get that definition under your belt. What does ionization mean? So it's the ease at which you lose electrons, okay? So in the sense of ionization energies, you have to mention the often countering factors of what's happened to the nuclear charge. Well, obviously, on descent of a group, the nuclear charge will increase because you've got more protons in that nucleus. But you've also got, as you descend, that extra, which often overrules it, which is that electron shielding. Okay, there is a way of shortening that word, I suppose, which you can say about effective nuclear shielding, as opposed to just discussing nuclear shielding versus nuclear charge versus electron shielding. You can just say and discuss the effective nuclear charge or effective nuclear shielding that takes place. Okay, but I'm hoping you all recognize that ionization energy on descent of any group, regardless of group 1 or not, decreases, and that's because you've got this shielding that overrides the increased nuclear charge. Okay, explain. Now this, again, as I said, it's interpreting the question. So you can see that this is an explain. So you're going to have to do exactly what it says on the tin. They're asking you to explain the trend. So it's then expanding on the fact that you are aware that potassium has, or as you said, the lower the group, has more shielding. Therefore, it's much, much easier due to that shielding to lose an electron. And that drives the greater reactivity. So as it says there, as the group descend, the outer electron is much more easily lost because of that shielding. So that's just a mark scheme, but I've hopefully covered it already for you. Now, okay, it was evident that most candidates had seen the reaction, but as I said, it is a comparison question and lots of pupils fell on that final hurdle of not reading what the question means. So they're asking you for a comparison or compare or what's the difference. You have to complete that question by mentioning both of them. You can't assume that talking about one, which was forgiven in GCSE, I'll be honest with you, it was. So if you described one in GCSE, it was assumed that the count argument would be true. You can't assume that in AS. They want you to expand on your answers and say both. Okay. So that is just the examiner's comment that came up. Okay, lots of people talk about atomic size changing and electron shielding, and those are both necessary to get full credit. Okay. Right, the next question that says the GCSE student said that apart from metallic bonding, bonds are either ionic or covalent. An A-level student said, that's not really true, and that bonds could be intermediate between ionic and covalent. Well, as I outlined earlier, most, in fact, compounds are a bit intermediate because they will have a difference in electronegativity. So the only true, I suppose, covalent bond is where the electronegativity is the same because you've got the same atom. So Cl-Cl, that is a covalent bond. Okay, that doesn't mean it never shows polarity, of course, because of van der Waals, but that is, in a sense, a covalent bond between two atoms of the same element. Okay, so you can see that question asks you, and I did emphasize in that earlier slide about being able to sketch and describe the electron density in each bond. So as I outlined earlier, the ionic is having the electron density around the ions themselves, but nothing in between. And then in covalent, you've got some electron density between the atoms. And in intermediate, yes, there's still some in between, but you've also got an uneven distribution. So it's more one-sided towards the most electron negative. Okay. So being able to explain and visualize the electron density is very, very important. Okay. All right. So you can see that these is what I hopefully outlined for you earlier in that slide where I tried to show you the sketches of electron density. Okay. It was one of the questions that actually, when it came out, caught out a lot of weaker candidates. Okay, so the instruction to state one factor meant that differences in electronegativity had to be discussed. Okay, this is what you're trying to avoid in AS, which is far less commonly forgiven. As I said at the very beginning, vague statements will not get you any marks in AS. They want clarity. They want clear definitions that are kind of telling them exactly what is being asked. Okay, so no wishy-washy vocab, no vagueness. Okay, you have to be clarity itself. Okay, and only able candidates recognise that the question being asked was asking for a description of electron density. So those sketches I said in one of the earlier slides, get that memorised, please. Okay. Draw dotted cross diagram to show the electron arrangement in hydrazine. Now, hydrazine isn't something that you've come across in year 12. You will in year 13. Okay. They can ask you anything because what they've done is they've given you the formula, and you're meant to recognise then that nitrogen and hydrogen do have the number of valent electrons, which you're familiar with, and you just have to put it together into the dotted cross diagrams. So they can ask you anything, okay? Anything they want, as long as they give you the formula. Right, the second part there of the question was asking you about what is meant by a polar covalent bond. They could have asked that about any polar molecule, okay? That they could have asked that about HCl, for example. So to answer it, drawing the dotted cross, you can see there that the 2 marks originated from having a clear shared pair of electrons between the nitrogen. So they were focusing on that one. And then the rest of the electrons being around. So they were focusing on the bond between the nitrogen and nitrogen primarily. But it's important to note here, note that you've got dots, cross and triangles, because it was felt by the examiner that it was important to show how the nitrogen electrons bond differently to the nitrogen, the other one, I mean, as well as the hydrogen. So they felt it was probably best to introduce a third symbol to give clarity to this answer. Okay. Of course, polarity or a polar bond is a covalent bond where there's that uneven distribution of charge. Whatever sits comfortably with you about defining polarity or a dipole, go with that one. Do not take what your teacher says necessarily, or what the kind of peers before you have said. Find something that's going to sit with you comfortably and use that one. Just check that it's correct factually, of course, but I'm sure you could dance around the same type of answer, but be more comfortable with one. So find your own definition, okay? All right, melting temperatures down groups and across periods, okay? So classically, why is chlorine a gas and why is iodine in the same group a solid? Well, again, you know it's to do with the van der Waals, but it's worth noting here that the number of marks means you have to be quite obvious in some of your statements. Otherwise, how are you going to log in, or how are you going to notch up 3 separate marks, of course? So you have to say 3 distinct things. So I would start by expanding on things like that. You're aware that iodine has more electrons than chlorine because it's obviously lower down in the group, and as a consequence, it will have a greater van der Waals force being present. Okay, so that would be kind of 1 mark. But this is something that is, and it doesn't really matter whether it's GCSE or AS, it's the same mark that gets missed all the time. If they ask you to discuss melting temperatures, it's nearly always the case with weaker and even intermediate candidates that they lose 1 mark because they don't refer to the part of the question that asks you about melting temperature. So you can expand on, yes, I've got more van der Waals forces, I've got more electrons, but you have to then tie it all together and say, as a result, it will need more energy to break apart. That's the relevance of melting temperature. You're fundamentally asking, why is it harder or easier to break a bond? So if you don't feed back and go back to that original statement of how that van der Waals affects the melting temperature, you've lost 1 mark out of that 3 automatically. Okay, so I said earlier, classically, why is sodium not as metallic then? So why does it have a lower melting temperature than aluminium? Again, it's going back to this, how many valent electrons you have in that sea of electrons when that metallic bonding is created. Aluminium, obviously, per atom has 3, comparable to every one of sodium only having 1. So it is therefore got a much weaker electrostatic attraction present in that. And therefore, you have a lower melting temperatures for sodium because it's easier to take those ions apart because the attraction electrostatically between them is weaker. Okay, so classically, that's 1 mark. It is worth noting, and hopefully I'll just about get it in at the end, there's a near identical question that was asked 2 years later, but it was worth 3 marks. Okay, so silicon, it's got a high melting temperature than phosphorus. This is going back to something you picked up in GCSE. Silicon is a giant covalent structure, okay, whilst phosphorus is a simple molecular one, so it has naturally has a lower melting temperature. Okay, so this is the key thing that, as I said, classically we get mistaken with, okay, is that they forget to mention, oh, I've pressed the wrong thing, apologies. They forget to mention this crucial bit here, which is how it affects the temperature, okay? Aluminium has more valence electrons than sodium, therefore has stronger metallic bonds because it's got a more dense electron, sea of electrons. And then silicon has a giant molecular structure, but phosphorus has weaker, simple molecular forces present. Okay, but very next question came a few years later, admittedly, but it's nearly an identical question. It's asking you, why has aluminium got a higher melting temperature than sodium? But look, it was worth 3 marks, and they threw in, for good measure, a QWC question. Okay, so take a judgment from that, how much they want, and this will be the last question I review with you. But it's going back to that diagram I showed you earlier, okay? Right, I'm going to skip a few, but please take advantage of the fact that these resources are shared with you after the session, and therefore please go through the PowerPoint, stop it, attempt these questions yourself. But I'm going to quickly go to the last few slides I have, which just to encourage you as Year 12 candidates to use the resources that are out there. Okay, so for example, this is the knowledge organisers. They were present for GCSE. They're again present for AS and will be for A2. They use them. They're written by the exam board. They've got the key points that are important for each topic. Therefore, they might not be comprehensive. They might not cover everything. Don't think that they do, but they are certainly a good starting point to your revision plan, isn't it? So work around these sort of knowledge organisers. Try varying your revision. So this is a kind of quiz, an online quiz called Quizlet. Okay, I've put the link on there so that when you click on it, it will take you to the one that's relevant to topic 1.4. Okay, so it brings on things like flashcards. It's got a matching game there and all these sorts of stuff. Okay, so all in all, just embrace your revision. You should be starting it from probably now onwards, if I was honest with you, haven't already done so. But try varying it, okay? We appreciate that AS chemistry is challenging, but try making it as enjoyable as possible. So that's it for me this week.